Welcome back to G Fun Facts Online. Today, we are not just talking about a new gadget or a faster chip. We are talking about a fundamental shift in the physics of our universe, or at least how we manipulate it. For 60 years, physicists have been chasing a ghost. It is a dream of combining two different worlds. On one side, you have the world of logic, the semiconductor. These are materials that resist, switch, and calculate. They are the zeros and ones of our digital lives. On the other side, you have the world of infinity, the superconductor. These are materials that flow, are eternal, and perfectly efficient. To combine them was to dream of a computer that could think without heat, a quantum machine that could be built on a factory line. For decades, nature seemed to have a rule against this union. But in late 2025, that rule was broken. The material at the center of this revolution is not some newly discovered alien element. It is the forgotten ancestor of the Silicon Age, germanium. Today, we are diving deep into the Germanium Breakthrough. Let's start by setting the stage with the impossible marriage. To understand why this is such a big deal, you have to understand the Berlin Wall that has existed in materials science. On the left, we have semiconductors, like silicon and germanium. They are the bricks of the digital age because they represent a struggle. When you push an electron through a semiconductor, it encounters resistance, it fights its way through. That struggle is useful because it means we can stop the electron, start it, and steer it. That ability to switch current on and off is what makes logic possible. It is the basis of every computer you have ever used. Now look to the right. There, we have superconductors. These are usually metals, like aluminum or niobium. When you cool these materials down to extreme temperatures, they undergo a magical transformation. Resistance vanishes. Zero. Nada. Electrons inside a superconductor pair up into what we call Cooper pairs. They flow endlessly without losing a single atom of energy. If you start a current in a superconducting loop, it will flow forever, potentially outlasting the universe itself. For half a century, scientists have looked at these two worlds and thought, what if we could combine them? A superconducting semiconductor would be the holy grail of electronics. It would allow us to create Josephson junctions, which are the heart of quantum computers, out of a single block of material. Currently, quantum computers are built by smashing a superconductor onto a semiconductor. It is a messy, chaotic interface where metal meets silicon. It causes signal loss, heat, and errors. But if you had one material that could do both, you would eliminate that interface. You could build Germanium qubits that are fast, tunable, and scalable. But as I mentioned, nature had a rule. You can have logic or you can have flow. You cannot have both. Usually, if you try to dope a semiconductor to make it conductive enough to superconduct, you destroy the delicate crystal structure. It shatters or turns into a disordered mess. But in October 2025, a team led by physicists at New York University and the University of Queensland decided to break the rules. They didn't just find a new superconductor, they forced germanium to become one. Let's get into the anatomy of this discovery. This wasn't an accident. This was a feat of atomic engineering. The team, spearheaded by Professor Javad Shabani, focused on germanium. Germanium sits right below silicon on the periodic table. It has a similar diamond-like crystal structure. The theory was simple. If you flood germanium with holes, it should become a superconductor. Now in physics, a hole is the absence of an electron. It acts like a positive charge carrier. If you pack enough holes into the material, it transitions into a metallic state. The problem is the packing. To create these holes, you have to replace germanium atoms with gallium atoms. Gallium has one fewer electron than germanium, so every time you swap one in, you create a hole. But gallium atoms are smaller and softer. Past attempts to force gallium into the germanium lattice resulted in the structure collapsing. It was like trying to build a brick wall where every eighth brick is made of marshmallow. The wall eventually crumbles. The breakthrough came from a technique called molecular beam epitaxy, or MBE. Imagine a spray painting machine, but one that sprays individual atoms in a vacuum so perfect it mimics deep space. The researchers didn't just mix ingredients in a pot. They grew the crystal layer by atomic layer. They carefully controlled the temperature and the flow of atoms to trick the germanium lattice. They managed to substitute 1 out of every 8 germanium atoms with gallium. This is an insanely high doping concentration. In normal electronics, you might dope 1 atom in a million. 1 in 8 should NT be possible. Under normal circumstances, the germanium would reject the gallium, pushing it out into clumps. But the MBE process froze the atoms in place before they could rebel. The result was a thin film of supergermanium. When they cooled this film down, they watched the resistance drop. And then, at roughly 3.5 Kelvin, or minus 453 degrees Fahrenheit, it flatlined, 0 resistance. The germanium was no longer a semiconductor. It was a superconductor. But why does this specific material matter so much? Why not just use a new metal? We have to look at history. In 1947, the first transistor was built at Bell Labs using germanium. For the first decade of the computer age, germanium was king. But it had a flaw. It was unstable at high temperatures and didn't form a good natural insulator. Silicon, on the other hand, forms silicon dioxide, which is a perfect insulator. So, by the 1960s, silicon took over, and germanium was cast aside. But germanium never truly went away. It is inherently faster than silicon. Electrons move through it with much higher mobility. Now, with the discovery of superconductivity, germanium has an advantage silicon cannot match. Silicon acts as an insulator for superconductors. It kills the quantum state. Germanium, however, can now be the superconductor. This means we can manufacture quantum chips, using the same machines and factories we already use for our laptops. We don't need to invent a new industry. We just need to retune the old one. Let's look under the hood at the science. What is actually happening inside this supergermanium? It comes down to Cooper pairs. In a standard superconductor, as an electron moves through the positive ion lattice, it attracts the ions slightly. This creates a region of higher positive charge, which attracts a second electron. These two electrons, which normally repel each other, become bound together. They form a Cooper pair. Cooper pairs are unique because they act like bosons. Unlike individual electrons, which cannot occupy the same space, bosons can all pile into the same quantum state. They move as a coherent wave, slipping through the lattice without hitting anything. No collisions means no resistance. In the NYU experiment, the gallium atoms played a dual role. First, they provided the holes needed to conduct electricity. Second, they modified the vibration of the crystal lattice. The high concentration of gallium created a strain. The atoms were packed tighter and under tension. This strain shifted the energy landscape, pushing the electrons into a zone where superconductivity is favored. Crucially, the research showed that this material has a hard gap. In quantum mechanics, the gap is the energy required to break a Cooper pair. A soft gap means some rogue electrons leak through, causing errors. A hard gap means the protection is total. This is vital for quantum computing because it means the data stored in this material is protected from the noise of the outside world. This leads us to the Holy Grail, integrated quantum circuits. Current quantum computers, like those from Google or IBM, are engineering marvels, but they are Frankenstein monsters. They usually feature aluminum superconductors sitting on top of silicon wafers. The interface between them is dirty. The atoms don't align, creating microscopic defects that trap energy and cause the qubits to lose their memory. With superconducting germanium, there is no mismatch. You can take a wafer of germanium, dope one region to be a semiconductor for control, and dope the next region to be a superconductor for the qubit. The interface is seamless because it is the same crystal. This allows for the creation of gate-mons. These are qubits that can be controlled by a simple voltage, like a transistor, rather than bulky magnetic fields. Imagine a chip that looks like a standard processor. Layer 1 has germanium semiconductor transistors for logic. Layer 2 has germanium superconducting qubits for calculation. Layer 3 has superconducting interconnects for data transfer. All made of the same material. All made in the same factory. This is the path to a quantum computer with millions of qubits, not just hundreds. But the applications go beyond quantum. We are entering the super-semi era. Think about cryogenic electronics. Deep space is cold. Current electronics on satellites are designed for room temperature and have to be heated up to survive, wasting power. With superconducting germanium, we could build electronics designed to work at 3 Kelvin. These chips would have zero resistance, generate no heat, and consume almost no power. This could revolutionize deep space probes. Then there are sensors. Superconductors make the most sensitive magnetic sensors in the world, called SKU-IDS. They are used in MRI machines. Currently, making them is complex. Making them out of germanium would make them cheaper and smaller, potentially leading to portable brain scanners. We also have terahertz computing. The speed of a computer is limited by heat. Run a silicon chip too fast, and it melts. Superconductors generate no heat. A hybrid germanium chip could potentially run thousands of times faster than today's processors. Of course, we must temper the hype with reality. There are challenges. The first is temperature. 3.5 Kelvin is incredibly cold. It is close to absolute zero. To reach these temperatures, you need massive dilution refrigerators. While this is fine for a quantum computer sitting in a data center, it is a deal breaker for consumer electronics. You won't have a superconducting phone in your pocket anytime soon. However, the hope is that understanding this mechanism could lead to high-temperature variants that work with liquid nitrogen. The second challenge is manufacturing cost. The molecular beam epitaxy technique is slow. It is a research tool, not a mass production tool. Engineers need to figure out how to achieve this high doping using standard industrial processes like chemical vapor deposition. If they can't, this will remain a niche technology. Finally, there is strain management. The crystal lattice of supergermanium is under immense tension. If the film is too thick, it snaps. This limits the technology to very thin layers. Engineers must learn to build 3D structures without losing the magic. Despite these hurdles, the germanium breakthrough arrives at a perfect time. Moore's law is dying. We can't make silicon transistors much smaller. The industry is looking for more technologies that add value through new physics. Superconducting germanium fits this perfectly. It integrates the next generation of computing with the current one. Looking at the roadmap, the next few years will be about optimization. Researchers will race to raise the critical temperature. By 2028, we might see the first all-germanium qubit. By 2030, we could see hybrid chips in pilot production. In conclusion, for 60 years, germanium was the sleeping beauty of electronics. It was potent but slumbering in silicon's shadow. With atomic spray painting and precise gallium injection, the sleeper has awoken. It has woken up not just as a semiconductor but as a superconductor. This forces us to rewrite the textbooks. The line between the two worlds has been erased. We are standing on the precipice of the hybrid era, where chips don't just compute. They cooperate with the quantum nature of the universe. And perfectly enough, the key to the future was hiding in the very first transistor we ever built. That's it for today's deep dive on G Fun Facts Online. Thanks for listening.